Good morning, Sarah. Good morning, everybody. Hope you're all doing well. My mind is like so confused by this weather. The last 2 days, it was so amazing. Hopefully you got outside for a little bit. I took my daughter out. It felt like spring. I was like, yeah, I'm over winter. Let's do this. And then we have today. And then I remembered it was January and I was getting a little bit overzealous there. So it can't be winter forever though. And it hasn't been that bad. And honestly, I'm from Chicago where winters last like 6 months and they're a true 6 months. It's not like here, here you get to wear a hat because it looks cute and a scarf because it looks cute, not necessarily because you need to. So, all right, let's do some chemistry. My husband was having some trouble with our internet yesterday. So let me know if at some point it's like, it seems like it's skipping or you can't hear me because I just want to make sure you have a good connection. Okay. So we were on chapter 3 and we were talking about the universe and we got through the matter section of it. So now we're going to move into energy. So energy is what gives matter its it's what makes it interesting. It allows objects to move. It allows things to stop. And then if we go into a more physics-based definition of it, it's anything's ability to do work. And work, we mean more in the scientific sense. So not like, oh, I've got to go to work, but like a force over an area. So there's different types of energy, or we can classify it in different types of ways. The first one, which I think is the easiest for people to understand, is kinetic energy. This is the energy that's associated with motion. So if something is moving, it has energy just merely because it's moving. So swimming, water flowing down a dam, working out, anytime your body's in movement or atoms and molecules are in movement, they're gonna have some sort of energy. You can feel that energy if somebody is running and then you stand right in front of them and they run into you. You'll feel that energy. We keep this picture of the dam when talking about potential energy because let me actually go back here. So the water that's right here where it's falling, this has a lot of kinetic energy to it, okay? This up here doesn't have a whole lot of kinetic energy. It's got a little bit, it's like kind of rolling towards the edge, but this water up here actually has what's known as a lot of potential energy. So potential energy is energy that is stored in the matter and can be used at a later time. So the water at the top of this dam has a certain amount of potential or stored energy because it's higher up. Another potential energy example is a spring that you've compressed. So if you take a spring and you use the energy from your breakfast to squeeze it together, now that spring is holding a stored energy. And at any point you can let that spring go and it's going to pop open. And then lots of potential energy stored in chemical bonds. So when we break a chemical bond, like let's say 2 carbon atoms that are connected, if we break those, they'll produce energy. Gasoline has a lot of potential energy, coal, and then food, right? We eat food, it gives us energy. Our bodies are able to break it down to give us energy. So all of these different types of energies, there's other ones outside of kinetic and potential, can transfer into each other. So the water up here has a lot of potential energy. When it moves over the edge, that potential energy starts to decrease because it's no longer high up above sea level, it's moving towards sea level. So that potential energy actually swaps out for kinetic energy. It begins to move. So define these as either potential or kinetic. Rollerblading is kinetic. Anytime you move, you're kinetic. Think about kinesiology. When someone's a kinesiologist, they're studying the motion of the body. Peanut butter and jelly sandwich, unless you're throwing it at somebody's head, that has potential energy. Mowing the lawn is kinetic, and gasoline, when it's in the gas tank, we say that has a lot of potential energy. So when we're talking about energy, we need a unit for it. Heat is the energy associated. So we'll talk about heat and units of energy, actually. So first, heat. So the word heat is not, people get heat and temperature kind of mixed up. Temperature is measuring the random motion of atoms or molecules within an object. Heat is the energy associated with the transfer of particles or movement of particles from transfer of energy from one thing to another thing. So this is measured in joules or calories. This calorie here with the lowercase c, that is not a nutritional calorie, okay? There is a conversion between little c calories and the capital C calories or big C calorie. A big C calorie is a nutritional calorie, and we'll do a couple conversions on that. So the faster that the particles are moving, so the higher that the temperature is, the greater the heat or the thermal energy. So temperature and heat are related to each other, but they're not the same thing. All right, so let's look at some of the units. So we've got the SI unit, which is the joule, which you'll see quite often. Because it's an SI unit, we can put prefixes in front of it. So we can have a kilojoule, we can have a millijoule, we can have a terajoule. So just know that the joule would act as a base within that. Here we've got the kilojoule. Kilojoules is equivalent to 1,000 joules. Same thing with our other prefixes. Then we've got this here. So 1 little c calorie is equivalent to 4.184 joules. And that number 4.184 is exact, and you're going to want to have it available. And you'll see that number pop up in other places as well. So anytime we have two things that are equivalent to each other, it's a conversion factor. We can write it in multiple ways, and we can do dimensional analysis. This right here, so the calorie, the little c calorie, is equivalent to, I don't know why this should have, I don't know why they didn't capitalize it here. So the units for the bold calories here, I want to put a big capital C. Okay, the capital C is equivalent to 1,000 of the little c calories. All right, or 1 big C cal is equivalent to 1,000 little c calories. The big C calorie is the nutritional calorie. So energy comparisons. Okay, so let's do a conversion. Here it says, how many calories are obtained from a pat of butter if it provides 150 joules of energy when metabolized? Oh. And this is asking about little c calories. And while you're at it, also solve for big C calories too. So also solve for big C, big calorie. Okay, so this is a very, very small amount of energy, 150 joules, super tiny. This isn't like a pat of butter. It would be like a very tiny amount of butter. But so we're going from joules to calories, little c calories first. So 1 little c calorie is equal to 4.184 joules. So we have 150 joules. We convert it to 36 little c calories. If we wanted to then convert this to nutritional calories, I would go for every 1 nutritional calorie, it's got 1,000 little c calories. So we would divide it by 1,000 or move the decimal over 1, 2, 3. So it would end up being 0.036 nutritional calories. That's why when I say 150 joules is a small amount, think about how many calories that is. That's non-existent. So let's do, let's see what the slides have here first, and then we may go back and do another calculation. So energy and nutrition. So use the energy values to calculate the kilocalories or kilojoules for food. So what is a calorimeter? A calorimeter is a way to measure the amount of calories in a certain amount of food. So if you've ever kind of wondered, oh, like how do they know that candy bar has 225 calories or 225 little c kilocalories? They use this thing called a calorimeter, and it's a way to measure the transfer of heat. So we have some sort of container, usually a steel container filled with oxygen, and then there's a specific amount of water in it. They will burn or combust the food, and the food will transfer its heat into the water, and the water will gain temperature, right? How much temperature the water increases will tell you how many calories there are. So if you increase the water by, like 1 degree, that's not going to be as many calories in the food as if you were to raise it by 4 degrees. So here's what the contraption looks like. So we've got a sample of food. Here's some sort of way to ignite the food without adding any sort of mass to it. So we don't want to put something that needs to burn. We just want to burn solely the food. It will produce heat and it will distribute it into the water. And there's some sort of thermometer attached that will increase in temperature. And there's usually a turbine to mix so that it's evenly mixed. So if this is a really big sample of food, we're going to expect to see that temperature go up than if it's a smaller amount of low calorie. So we've got the big C calorie equals 1,000 of those little C calories, or 1 big C calorie equals 1 kilojoule. So what you're seeing on a food bar, a nutritional facts on the side of your food, you're seeing a kilocalorie. Some places will also express their food as kilojoules if you're in a different country. So if you were to see the kilojoule, you kind of know the relationship between those two, right? It's this 4.184 relationship. So let's do a calculation. I want to know, I've got a candy bar. And it has 350 nutritional calories. Okay, so it's not the biggest candy bar there, but it's larger than the small guy. So I want to find joules. Okay, so tell me how many joules are in that thing. I'll give you all just like 2 minutes for it. It's very similar to what we did on that last problem, just in reverse. Okay, so we're given that we have a candy bar and it is 350 nutritional calories, and I'm trying to find joules. So as far as a flow chart or my thought process, I'm gonna go from big C calorie to little c calorie, and then from little c calorie into joules. So big C calorie, 350 of those. How that relates to little c calorie, because we're going to do our first hop. Well, for every big C calorie, we get 1,000 of those little c calories. Now I can relate little c calorie to joule. For every 1 little c calorie, I get 4.184 joules. So the little calories cancel and the big calories cancel, and we're just left with these units of joules. And actually, I'm not going to write joule out just yet because I have a feeling this is a large number, because food actually carries a lot of joules to it. So give me just a second. So that 350, we multiply it by everything on top, and then we divide it by anything that's on the bottom. In this case, we don't have it. We don't have anything but ones. So we get 1,464,400 joules. I'm going to refine this. I'm going to round to 2 sig figs because we have 2 sig figs in our given. So I'm saying 1 and I'm writing 4. 1,500,000 joules. And then I'm going to take it even a step further and write it in scientific notation. 1.5 times 10 to the 6th joules. Hopefully these conversion problems are starting to feel kind of simple, like it's the same setup, it's just different conversion factors, right? And again, how many conversion factors are there out there? There's thousands and thousands and thousands of them. So it's just making sure that you're setting it up in such a way that the canceling happens. If you do that and you use the right conversion factor, you should end up with the right answer. Okay. So another thing that I want to talk about, these are important. So the caloric energy given in each gram of food is another relationship that we want to talk about. And you may have seen this number on the back of a food container as well. But carbohydrates will always or consistently give you 4 kilocalories or 4 nutritional calories in every 1 gram of it. So if you have 1 gram of any sort of carbohydrate, it will contain 4 calories always. Fat, on the other hand, will contain 9 kilocalories or 9 nutritional calories in every 1 gram of it. Protein is also 4. So remember 494, 494. You will see that on your lab that you're working on. And in the lab, you actually will have to grab some sort of food from your pantry. So you'll be able to practice with this. But this is one reason why, you can eat a lot more carbohydrate and protein than you can fat. And I don't just mean like, fat's bad, fat is good for you, but you could eat a bowl of carbohydrate. You probably couldn't eat a bowl of fat. Like you can eat a bowl of pasta, you can't eat a bowl of butter. It would make you sick because it's just so much more calorically dense. So, you get a pat of butter as opposed to a bowl of butter. So here are some of the breakdowns of the different types of things we have. So 1 banana. A banana is mostly, yes, this is true, Sarah. A banana is mostly carbohydrate. There's a little bit of protein in there and there's no fat. So you get 26 grams of carbohydrate. These values here, these gram values actually do relate to the amount of energy. So let's look at this. Okay, 26 grams of carbohydrate. How many calories do we get for every gram of carbohydrate? We get 4. right? So 26 times the 4 means that there's 100, roughly 104 calories are coming from carbohydrate. Protein, we also have that 4 ratio, right? 4 for every 1 gram. So we're getting 4 grams from protein. So we add those together, we get a total of 108 calories, which is close to 110, right? So you can actually know how many grams of each of these you have, and you could calculate the total calories. Let's do one that's we can do the steak down here. Okay, so 3 ounces of steak. So steak contains a lot more calories. It's much more calorically dense than some of these other things. Why? Well, it doesn't have any carbohydrates. It has 27 grams of fat in it. So if I take 27, what do I have to multiply my 27 by? Not 4, I have to multiply it by 9, because we get 9 calories for every 1 gram of the fat. So in this one, it's 243 calories are coming from the fat. And then we have 19 grams of protein. And that is, in fact, still 4, right? So 4, 4, and 9. This becomes 76. When I add those two together, 243, you get 319 calories, which is close to the 320. So you guys starting to see how you can add these up to get the total calories. You will have to do a calculation like that. We'll try that out. So the more fat you have in something, the amount of energy or the total calories is going to go up much quicker because you get more bang for your buck with fat. So guide to calculating energy from food. State the given and the needed quantities. Use the energy values for each food type to calculate the kilojoules, rounding off to the tenths place. Add the energy for each food type to the given total amount of the food. So we'll look at this one here. A cup of whole milk contains 13 grams of carbohydrate. So go ahead and write down 13 grams of carbohydrate, 9 grams of fat, and 9 grams of protein. How many kilocalories does a cup of milk contain? And kilocalorie meaning nutritional calorie. And remember, our relationship here is that for every 1 gram of carb, we end up with 4 big C calories, right? For every 1 gram of fat, we get 9 big C calories. And for every 1 gram of protein, we get, again, 4 calories. So these are your dimensional analysis conversion factors. So I'll give you a minute to go ahead and calculate the amount of calories in milk in a cup. right. So you want to take each of your 3 values and multiply them by the correct conversion. So 4, 9, and 4, make sure the 9 is going with the fat. To convert, right, we've got gram down here and gram down here. The kilocalorie will stay on top. So you want to multiply them by each other so that you're left with the kilocalorie, the nutritional calorie. So 52 nutritional calories from carbohydrates, 81 from fat, and 36 is coming from protein. The final step is you just want to add those all together. And in this case, you get 169 kilocalories. The back of your milk container would probably round that up to 170. So you may notice when you're calculating these, like when you do it for your lab, that it's not exact, that you're off by a couple calories. That is okay. So the number of kilocalories or kilojoules needed for your daily diet is varied greatly for a lot of different reasons, depending on your activity level, your age, your sex at birth, right? Lots of different things that can cause how many calories you want to be eating. Moderately active, somewhere in the 2000s. More active, you add calories from them. Look at this. Look how great this is. You actually burn calories doing some everyday things. Sleeping, you burn 60 kilocalories an hour. That's great. I could do some more of that. Obviously, you burn more if you're running. And then it says a person loses weight when food intake is less than their energy put out. So you need to be doing more of this and less of this to lose weight. Obviously, it is much more complicated than that. So the quality of the food that you're eating as well is very, very important. So this is kind of an oversimplification. Okay, so we've got another word that has heat in it, and it's called specific heat, but it is not the same thing as heat, okay? It's related to heat. Specific heat is a property of a given type of piece of material or matter. So water will have its own specific heat, hence the word specific. It's specific to the material. It's the amount of energy required to raise like a gram of that thing by a degree Celsius. So we've got a picture here of a coastline. Coastlines in general tend to be more moderate in temperature, right? They're cooler in summer and they're a little bit warmer in winter. Why is that the case? It's because there's a huge body of water next to the coast, which acts as an insulator. Water has a very, very high heat capacity, meaning it takes a lot of energy to heat it up, and it takes a lot of energy, or it has to release a lot of energy to cool it down. So it creates this sort of nice buffer situation. So as far as specific heat is concerned, it's different for different substances. So water has its own specific heat. Gold has its own, all of them do. Not only does water have its own specific heat, but water versus liquid versus ice versus steam, all of those will have their own specific heat. So to raise liquid water by 1 degree Celsius, it requires less energy than if I wanted to raise steam 1 degree Celsius because it's at a higher temperature. So it's the amount of heat or energy needed to raise 1 gram of a substance 1 degree Celsius. It has funky units, and you need to include all of them. Joules per gram degree Celsius. Okay. In this class, so if you were in 092, you kind of stayed just with these units. But we will also add this. This is another possibility, which is calorie per gram degree Celsius. Very similar to the first one, except instead of having joules on top, we have calorie on top. Okay, you are going to have to be able to use either one of those. So here it is. We've got our specific heat. It's going to be the amount of heat over grams times the delta T. For water, it is 1 calorie per gram degree Celsius, or 4.184 joules per gram degree Celsius. That's the amount of energy it takes to raise 1 gram, 1 degree Celsius. So have those numbers written down on your formula sheet or somewhere that you will be able to access that. Look at that 4.184. That's the same number as the conversion between calorie and joule, right? So conceptually, if you know this, you should be able to get this, or if you know this, you should be able to get that. So let's look at a couple different specific heats for different substances. Aluminum, right, has 0.897 joules to raise 1 gram, 1 degree Celsius. Down here, we can see water has 4.184 joules per gram degree Celsius. So a lot more energy to raise 1 gram of water than it is to raise any of these metals. You see that in everyday life when you're boiling a pot of water. Let's say we have a copper pot. The copper pot will get hot much faster than the water does, right? The copper pot can get hot within minutes. The water, it doesn't seem like it ever boils. It takes forever because it's got to pump a lot of energy in that water to make it happen. Notice that if you have solid water, so this would be ice, it requires less energy. And then if we have gaseous water vapor, it's actually going to be more energy than those. So conceptually talking, let's see what we have here. When the ocean water cools, the surrounding air will actually warm. Why? Because there's a change in, or a transfer in energy. So in winter, when the ocean water starts to cool down, it's going to release heat to the surrounding environment, and that's what gives the coastline this more moderate temperature. Sand in the desert is hot in the day and cool at night. Sand must have a very low specific heat. It's very easy to heat sand up, and it's very easy for it to cool down. So you get that kind of oscillation in temperature day and night. You don't get that with water, right? If you go into the ocean at night, it's not like all of a sudden the water is cold. Whatever the temperature of the ocean was during your day swim, it should be the same at night. So if we wanted to calculate specific heat, or if we had specific heat and we wanted to calculate some other thing, we can use this heat equation. This is not a dimensional analysis problem. So when we're doing specific heat stuff, we're not doing dimensional analysis. It's a plug and chug. It's an equation. So the equation is heat equals mass times temperature change times specific heat. I'm going to arrange this in a slightly different order, just because I think it just sounds better. I call it Q equals MCAT. Q equals M cat. It's just a way to memorize it. Q being heat, mass is M, so that's in the same place. I just flipped these two. So C is the same thing as specific heat, okay? So sometimes this is called C. At, the AT in the cat, is the delta T, or the change in temperature. And Q equals MCAT. Now, remember, specific heat and heat are not the same things. Okay, specific heat is a characteristic of a given material. It's the amount of energy to raise 1 gram, 1 degree Celsius. It's related to heat, but it's not the same thing. Heat is the amount of energy absorbed or released. So when you're running these equations or these problems, make sure you're not confusing those two things. So specific heat will have the funky units. You may have problems that ask you to do it with the calorie per gram degree C. You may have some problems that give it in joules per gram degree C. If the unit over here has degree C, your temperature change also needs to be in Celsius, all right? Make sure those units match. So if the problem gives you the temperature in Fahrenheit, you gotta convert it to Celsius. Same thing with grams. So it's per gram, so our mass needs to be in grams. So if they give it to you in kilograms, make sure you're converting it to grams. If the specific heat that you're using is in calories, your heat needs to be in calories. If the specific heat is in joules, your heat will be in joules, okay? So just make sure you're allowing all the units to match up properly. how many the one thing I want to talk about too, temperature change. This is going to be T final minus T initial. All right, T final minus T initial. So if your final temperature is smaller than your initial temperature, which means the thing is getting colder, your value for heat will be negative because your change in temperature can be negative. That's okay. Your delta T can be negative. If your change in temperature is negative, your heat will be negative. All that's telling you is that the heat is being released or it's exiting the system. When your heat is positive, it means it's taking the energy on. So don't be freaked out by negative numbers in this. Always final minus initial too, F minus I. Any questions on that outside of, like, obviously we're going to practice it, but just what those things mean. So this is an equation that has 1, 2, 3, 4, well, really 5 variables because you have 2 temperatures. So 5 variables. So I would give you 4 variables and you would solve for the 5th. I could, ask you to solve for any of them. Astrid, confused about the difference between temperature and heat. Okay, so temperature is measured in Celsius, Kelvin, Fahrenheit. Temperature, conceptually what temperature is it is the random motion of the particles within a given object. So like your pan, your hot pan, its particles are moving at a certain speed. And there's a certain amount of collisions. So if it's hot, it's going to have more collisions, which will make your temperature go up. Heat, on the other hand, over here, this is energy. This is about transferring. So it's how much energy is transferring from the pan to the surrounding environment. So is that pan releasing a lot of heat to your hand and the air around you, or is the pan just releasing a little bit of heat? So, when your pan is, you just put it on the stove and you put your hand in the center to feel if it's warm enough for the egg. And if it's not giving off a lot of heat, it means its temperature is low. So they're related to each other, but temperature is about the object by itself. Heat is about the transfer of that energy to the surrounding environment. So this is sort of characteristic or innate to just the object you're looking at. Heat is talking about the object with its surrounding environment or how much of that energy is moving out. Does that make more sense, Astrid? Okay, cool. Yeah, I know there's all of them seem sort of similar, right? So we've got temperature, which is the collisions that are happening within a given object, heat, which is the transfer to the surrounding environment or absorption from the surrounding environment. And then specific heat is a characteristic specific to that material. It's a property. So let's do some of these. So as far as solving for these are not dimensional analysis problems unless you have to do an initial conversion factor. Otherwise, just state the given and the needed quantities. Calculate your change in temperature if that's not already done for you. Sometimes the problem will say the temperature increased by 3 degrees, then you won't have to actually calculate it out. Write the equation, put the values in that need to be put in and solve. Oh, I did want to give you one other thing. So we had one of those little isolation triangles for density. Let's do another one for this. So cut it sort of in half and then make 3 compartments on the bottom. We're going to put Q on top, then put mass, change in temperature, C. Put C, so it's cat. And then change in temperature. Remember, this is a multiplier bar. These are, that's a divisor bar. Come on, Candace, focus here. Divisor bar, and then these guys are the multiplier bars. So if I want to isolate for a given variable, I can use my triangle here. If you don't put these in the right place, it's not effective. So make sure you've got them in the right place. So if I want to solve for Q, that's this times this times this, right? Q equals MCAT. What if I want to solve for mass? Mass is going to equal, well, I've got everything that's left over, right? So I've got a Q on top, I've got a C on the bottom, and I've got a delta T on the bottom as well. And these two are multiplied by each other. If I want to solve for, let's say, delta T, sorry, the annotation on this is not as great as that whiteboard I use. So the delta T over here is going to be equal to everything that's left over. So we've got Q on the top divided by the mass times the specific heat. If you're good with isolating variables, you don't really have to worry about this, but that's just a nifty trick if math is not your favorite thing. Okay, let's do a problem. So what is the specific heat if 24.8 grams of metal absorbs 275 joules of energy and the temperature rises from 20.2 degrees Celsius to 24.5 degrees Celsius? So we'll work on this one together. I'll give you 40 seconds to write the problem down. Okay, so when I'm looking at this problem, I'm seeing the words heat, specific heat, energy, temperature change. So I'm going to just write out Q equals MCAT. That kind of triggers in my mind that I need to be finding all these variables. So given information, the first thing that it says here is 24.8 grams. So that's my mass, 24.8 grams of metal absorbs 275 joules. So this is where it gets a little tricky, where people are like, is that heat? Is that specific heat? Well, it's asking for specific heat. The unit of joule or calorie, when you have just the energy thing by itself, that's talking about Q. Okay, so we have Q, all right, this equals the mass. Q, 275 joules. We have a change in temperature, which is equal to 24.5 degrees C minus 20.2 degrees C. Always the final minus the initial. So what is that? 4.3 degrees C. And it says, what's the specific heat? So we're trying to find specific heat, SH, or that C value. So this is the thing that we want. So I've got to get it by itself. C is going to equal Q over my mass times my change in temperature. Looking at these units, they make sense: gram, joule, degrees Celsius. So I'm going to just literally plug it in. So where is my joule? It's that Q value, 275 joules. Put that over my mass, which is 24.8 grams times the 4.3 degrees Celsius. What you're going to see is that none of the units cancel, right? There's no joule to cancel the joule or gram to cancel the gram. And that's okay, because we're dealing with C, or we're dealing with the specific heat. Specific heat has the funky units. So we do carry all of those units with us. So in this one, you're going to want to take your top value, which is 275, and you're going to want to divide it by 24.8 times 4.3 in parentheses. Or another way you can do it is just take 275 divided by 24.8 0.8, 275 divided by 24.8, equal it out, and then divide it by, again, the 4.3. If you want to avoid parentheses or you don't have access to parentheses on your calculator, just divide and then divide. So I get a specific heat for this thing, 3 sig figs of 2.58 in the units, joules per gram degrees Celsius. So what that's saying is it requires 2.58 joules to raise 1 gram of this material 1 degree Celsius. This does 2.6. Where did it get the 2? Oh, because of the temperature. Okay, yeah, so I guess we'd round it to 2 sig figs, 2.6. Any questions on that outside of, we need to practice? All right, I'm going to give you another one. Let's see. What mass of water absorbs 2,530 joules of energy and raises by a temp of 16 degrees C. Okay, so what mass of water absorbs 2,530 joules of energy and raises by a temperature of 16 degrees C? I'll give you all a minute for that. And if you're thinking there's only 2 pieces of information, where's the other information? You've got to dig through your formula sheet for that specific heat of water. All right. So what mass of water absorbs 2,530 joules of energy and raises by a temp of 16 degrees Celsius? So this problem kind of looks like it's a little bit skimpy on information. It's actually not, hopefully. Yesterday I taught a class, I taught a similar thing, and I totally forgot to give like a whole piece of information, and they actually couldn't solve it, but nobody said anything. So if you ever get to a place where you're like, I don't think we have all the information, let me know, because you might be right. So Q equals MC delta T. What mass? So we're trying to find mass. What are we given? We're given Q, that's heat. So anytime it says absorbs or releases and you see the unit for joule or you see the unit for calorie, that's Q. So Q is the 2,530 joules. What else is given here? We have a delta T. It already tells us, it says raises by. So that is our change in temperature. It doesn't matter what the initial temperature was or the final temperature. It already calculated it for us. So we're good there. What are we missing here? C, specific heat. Now, specific heat of water is one that I want you to have on hand. We're using joules here. So it's the 4.184 joules per gram degree C. If for some reason this was given in calories, you'd want to use the 1 calorie per gram degree C. So actually now we have all the information. We need to isolate for M. So mass is going to be equal to Q divided by the other stuff, C times delta T. So we'll put in our Q value, 2,530 joules. Real quickly, make sure the units all match up. So this is in joules, this is joules, this is C, this is C. So we don't have to do any conversion. I'm going to take my 4.184 and I write all my units in, because then I can watch them cancel out. And that's just more confirmation that I've done it correctly. 16 degrees Celsius is my change. Look at Celsius cancels, joule cancels, and then we're left with unit of gram, and gram is below this fraction bar and it's below this fraction bar. So the gram unit will actually plop back up on top, which is exactly the unit we want for mass. So 2,530 divided by that 4.184 and then divided by the 16. And come on, pen. There we go. Okay, so my mass should be 38 grams. Yep. 37.79, round to 2 sig figs. If you ever get a different answer, I am known to miscalculate things. So don't hesitate to throw it in the comments and say, girl, you're wrong. Okay. Questions on this? On Q equals MCAT? We are going to do, later on, we do a couple calculations, these things called heat curves, where we will use this again. So we'll get more practice with it. So I'm not trying to rush through it, but I want to make sure we get to the heat curve by next week. So if you get the kind of gist of it, idea of it, we will get more practice a little later. But any questions on specifics on like where this thing came from or why this is this? Going. Okay. Let's swing back over here. So changes of state. And when we're talking about state, we're talking about the phase of matter. So is it a solid, is it a liquid or a gas? Matter will undergo a change of state when it converts from one phase to another. So going from here, like let's go say we're going from a solid to a liquid, that is melting. In order to do that, it needs to absorb heat, right? Now the reverse is true if I want to go from a liquid to a solid. That would be called freezing, and that's when you release heat. So you can see the two different colors. Red meaning you're absorbing. So to go from here to here, you have to absorb. Anytime you're going to a higher energy phase, you need to absorb energy. Anytime you want to drop back down, you have to give off energy. So like for instance, this gas, if we want to freeze this gas, it has to release that heat. So every substance has what's known as a melting point, which is also the freezing point. Melting point and freezing point are at the same thing, at the same temperature. So for instance, water has a melting point of 0 degrees Celsius. It also has a freezing point of 0 degrees Celsius because melting and freezing are the opposite of each other. That occurs only at this temperature. Unless we add something like salt to it. So if you have a solid ice that's at like negative 55 degrees Celsius, you're not going to melt it until you first bring that solid up to 0 degrees Celsius. Once you get to the 0 degrees, then you have the option to melt. Same thing with freezing. I can't freeze until I've gotten to 0 degrees Celsius. So if I have a liquid, let's say it's in your bathtub and it's 100 degrees Celsius, this liquid water. I have to first drop that liquid down to 0 degrees Celsius. It has to get that cold, then I can start the freezing process. When you're at this point, this 0 degrees Celsius, and you're moving through a phase change, you are not changing the temperature. All energy that's getting pumped into it is going towards the phase change. Okay, so when I have solid ice and I'm melting it into liquid water, the ice and the water are both sitting at 0 degrees Celsius. The energy that's getting thrown in here is going towards the process of phase changing. So at that point, we're at what's known as we have this value called the heat of fusion. And this is the amount of heat released when 1 gram of liquid freezes, or it's the amount of heat needed or absorbed to melt 1 gram of the solid. So the heat released during freezing is equal to the heat needed during melting. Those are equal and opposite. So what are those values? To melt water or a heat of fusion, it's 80 calories per gram, or 334 joules per gram. Those are numbers that you want to have. To freeze water, you have to release 80 calories or 334 joules per gram. 80 calories per gram, sorry. So there's some conversion factors here. These two equations look very similar. Keep track of time. Okay, these equations look similar. The difference is that here it's a solid and the energy is on the reactant side. See where the arrow is? The energy is on the reactant side, meaning that the water is absorbing this heat. Here, there's the arrow. The energy is on the product side because the liquid water is giving that heat off. Do you notice how in this equation, for these values, there's no talk of temperature, right? With specific heat values, we had a change in temperature. We don't have a change in temperature here. The only thing that's happening during heat of fusion for water, either melting or freezing, is a change in energy related to the mass. It doesn't have anything to do with temperature. We're staying at our freezing point or our melting point. So let's look at a problem. I think these are easier to calculate than the Q equals MCAT ones. But if we are using heat to calculate a conversion factor or heat of fusion, state the given, state what you're trying to find, convert. Okay, let's just do one. So how many kilojoules are needed to melt 32.0 grams of ice at 0 degrees Celsius? So a couple things to indicate or to note here. It's talking about melting. So this is a phase change or a state change. So chances are we're not going to be using Q equals MCAT here. There's no talk of specific heat, so stay away from that. Another thing to note, it says we're at 0 degrees Celsius. So we are already at the temperature we need to be at in order to melt. So we like this. Yay. Give it a check mark. That's a good thing. We have the number of grams. So I have 32.0 grams of ice. I want to melt this thing. And I want to figure out kilojoules. So I'm not going to be able to get kilojoules right off the bat. I'm going to go from grams into joules and then joules into kilojoules. What's the relationship between grams and joules if we're talking about ice? Well, let's go to that previous slide. All right, so we've got here 80 calories a gram. We don't want to use calories for this problem. 334 joules a gram. So we get 334 joules of energy for every 1 gram. So let me write that. We have 32 grams is our given information. We also know that 334 joules per every 1 gram. This isn't explicitly given in the problem, but you want to have it written down somewhere so that you know it. So start with our given information, 32.0 grams of ice. I'm going to convert it using this here. We get 330, let me put that guy on top. 334 joules for every 1 gram. What happens to the grams? They drop out and we're left with units just of joules. Now the problem says, hey, I don't want joules, I want kilojoules. So let's go one step further. For every 1 kilojoule, 1,000 joules, right? So we take our number and divide it by 1,000. No talk of temperature here because we're just staying at 0 degrees Celsius. So 32 grams of ice. Well, for every 1 gram of ice, I get 334 joules of energy. And then I'm going to divide it by 1,000 so that I know it in kilojoules. And this says we have 3 sig figs. So 10.7 kilojoules of energy. 10.7 kilojoules of energy to raise 32 grams of water at 0 degrees Celsius. What if instead of 32 grams of water, I had 300 grams of water? Do you guys think it would take more or less energy to melt that? Well, if it's more ice, it's going to take more energy, right? So instead of plugging 300 or 32 in, let's say we change this to 300. It's going to increase all of these values. So it should require more energy. So I'm just going to throw it through the calculator. 300 times the 334 divided by 1,000. And we end up with 100 kilojoules. Okay, so as your mass goes up, the amount of energy required to melt it should go up as well. But there's no talk of temperature. So same thing that we did. Okay. I don't know why it doesn't convert it to kilojoules when it asks you for joules. Here it changed it to joules. Here it was in kilojoules. So. All right, so we're going to stop there. Don't worry, we're going to get more practice on this. We're going to actually take these two concepts and smush them together next week into a heat curve. If you have any questions, feel free to stay around. I can help you out. Make sure you're working on your labs for this weekend and homework, and yeah, enjoy your weekend. Woohoo! It was good to see you all. I'll see you next time. Okay, bye-bye. Cecilia, give me just a sec, okay, Cecilia, and we can chat about that. Okay, so you're having a difficult time understanding how melting and freezing points are the same when their melting and boiling points are different. We haven't talked about boiling yet. So boiling point is the heat of vaporization. Melting and freezing both happen around the freezing point.
But don't you need to add heat to melt? I guess like energy, which is heat to melt something.
Yeah, hold on one second. Let me share my screen with you. So this is kind of going into what we're going to talk about next week, but this is, let's say that this is when we boil or when we melt. So this is 0 degrees Celsius. So this is my melting point. Okay, this up here is 100 degrees Celsius. This is my boiling point. So you're saying these are different temperatures, right?
Yeah.
Okay, well, melting and freezing happen here. / freezing.
And how does snow stay on the ground if it's like, I just don't understand how they happen at the same time. Like how, like for instance, snow.
Well, they're not happening at this, they're happening at the same temperature. So this is where if you're going up in temperature or you're adding energy, you're melting. If you're going down the slope, you're freezing. They happen at the same, I don't mean they happen at the same time, but in the same conditions. So if we're at 0 degrees Celsius and I add heat, I'm gonna melt. If I'm at 0 degrees Celsius and I take away heat, I'm gonna freeze.
Okay. Oh, okay. That makes much more sense.
Okay. So yes, sorry, it's not happening at the same time, but it happens in the same conditions just by slightly change by adding heat or subtracting heat. Same thing here. This point is where we have vaporization or condensation. So right at that 100 degrees Celsius, if I add heat, I'm gonna vaporize or turn into a gas. If I take away heat, I'm gonna start to condense. And actually at these points, both phases are existing at the same time. So at 100 degrees Celsius, you'll have some you'll have some liquid and you'll have some gas. Same thing here at 0 degrees, you'll have some ice and you'll have some liquid. Now, the ice that we have that stays on the ground, that ice is colder than 0 degrees Celsius. It's somewhere over here. You know, it's probably like -5 degrees Celsius. So that's why you're just the ice.
That makes more sense. Thank you. All
right, any other questions?
No, that's it.
All right, Cecilia, have a good weekend.
Thanks, you too.
Bye.
Bye.
Lyric, what's up?
Sorry. With the when I go to Master in Chemistry, it says homework is due on the 7th. I don't have one for this weekend.
Yeah, then you shouldn't, because we haven't technically gotten through the whole chapter. So
oh, okay. And then for the lab, for the second lab, it says it was due on the 24th. Is that when I look in it says it was supposed to be due on the 24th?
Yeah, you had 2 labs due
on
the 24th. Okay. So in this class, you'll have weeks where you have 2 labs due.
Oh, okay. I need to
so just go ahead and get lab 2 done as soon as you can.
Yes, ma'am. Sorry about that.
Okay, no worries. No worries. I can give you credit for it. Just make sure to get it done as soon as you can. And then moving forward, look and make sure it isn't like a double lab week.
Okay. Yes, ma'am.
Okay. Okay. All right. Bye, Lyric.
Bye.